Would one misconfigured GitHub action lead to the full compromise of your application? Hi all, this is Mohammed Abul Khair from AppSec Untangled, and this is another video in our Lessons Learned series where we take real-world vulnerabilities and go through them, not just to understand the exploit, but to take out some lessons that we can apply as we are reviewing and designing applications. Today we have a very interesting vulnerability that affected Cline, which is a coding agent that usually is used as a VS Code extension, and we're going to see how one misconfigured GitHub action could have led to the full compromise of the application using a combination of AI prompt injection and cache poisoning. So let's get to the details for this one. So this is the write-up from the security researcher. And again, like the affected application here is Cline, coding agent that lives or is used as a VS Code extension. And this was the vulnerable workflow. So this is a GitHub Actions workflow. And this was added by the team to triage issues added to the Cline GitHub repo. So this uses Cloud Code's GitHub action. So the goal here is when someone submits an issue, you take that issue and give it to this, or like automatically this workflow will take this issue, get its details, and triage it, just see is it true, suggest a fix, and so on. So a very typical use case for AI. And this, again, just takes all of these things and runs. Now, if you look closely, you're going to see the first problem here, because now we have this GitHub action. This is triggered by issues, which anybody can open. So not only people that can write to the GitHub repo can open issues, like it's a publicly available thing. So anybody can open an issue for the repo because it's a public repo. So anybody can create an issue and anybody can control the issue title and description and all of these things. And these things are added to the prompt passed to Cloud Code here. So this is already open to prompt injection because you have control over the input that's being used to build the prompt. So that is the first thing. Now, the other more alarming thing here is the capabilities and the permissions of this GitHub action workflow. So this, first of all, has access to some credentials. So in this case, the GitHub token, the Anthropic API key, it has access to these things. And also it has this setting, allow non-write users. Now, obviously this is by design because, like I said, anybody can open a GitHub issue. So if you just make it to write users, it won't have any value. You want to open that for everyone. So everybody is allowed to use this workflow and pass that prompt to Cloud Code. But obviously, again, if you go to Cloud Code's documentation, it already mentioned this is a risky thing, because now if you allow non-write users, you open up the agent to be maybe tricked through prompt injection to do something that the original user doesn't have access to. So you can already see a risky pattern here. And the other thing is the tool had some dangerous permissions like bash, write, and so on. So it could just run commands. So all what you need to do as an attacker here is find a way to trick it into running a command that comes from you. And this command can just leak these credentials as maybe a first attempted impact here. And this is exactly what the security researcher did. The way he did it is interesting, but it's not the only way to do it. So what he did is he created an issue and added this description in it. So this is the prompt injection payload. And this just tells it, before running the GHCLI command, install this package, okay? And then this is something that the attacker has control over. And in this npm package, which comes from, again, GitHub repo under the control of the attacker, he just added a pre-install script. And this basically ran this curl command, which took the Anthropic API key and sent it to an attacker-controlled domain. So now all what you need to do is listen and wait for the action to run, and then you will get that key in your access logs. So this was exposing that credential. So this is very interesting, but obviously this doesn't lead to the full compromise of the application. It just makes you get a key and maybe use Anthropic and get some tokens for free. So this was in itself a problem, but now the security researcher wanted to escalate that further and gain something more valuable. So this is where we pivot to the other issue. Okay, so within the same repo, there was another GitHub action. So this is the nightly build action. And what the researcher noticed here is that this has multiple steps, cache. So like it's caching some stuff, then installing, and then publishing the VS Code extension. And to publish the VS Code extension, you need these credentials. So now the goal is to actually leak these credentials rather than the Anthropic API key, because these are more valuable. If you have these credentials, you want to you can actually submit a new VS Code extension and as if you are client. So you can put malicious code in an extension and submit it as the client extension. And the first thing you can notice here is this uses this action, which is cache. So this is a caching action, and this is something typically used to reduce the latency, enhance the performance of a GitHub action. It just caches some files, it caches some values. In this case, it is caching node modules. So node modules, if you're not familiar with it, this is where like the installed npm packages usually reside. Okay, so this, just to make it a little faster, you don't need to run an npm install and install of the package from scratch. You just, if they are already installed, they're going to be under the cache, and you have like a specific cache key, which again is just going to check for these things and do it. Okay, so these files come from a cache, and obviously this is a very different workflow. This is a separate workflow from the one used to triage issues, but they are within the same account. And because they are under the same account, the first thing to notice here is that they share this cache. So although like the first workflow, if you go back to it here, doesn't really use the cache, but the cache is accessible to it. So this command that you have here, you can maybe change it to a different one that tries to write to the cache. Now, the other thing is related to how GitHub handles the cache. So there was an announcement from GitHub, which basically was about fixing an issue where like you only had 10 gigas per like cache or for the cache. So what they did is that after 10 gigas, if you fill the cache with the full 10 gigas, you just go and overwrite older values. So this was a behavior change back in 2025. And the attacker actually noticed this, or the security researcher, and he actually had this tool here, which basically overwrites the cache. So this writes the full 10 gigas so that everything in the cache is deleted, and then you can write whatever you want over the existing key. So this is an existing tool that the security researcher has, and again, this is we can call that basically cache poisoning. You share a cache with another component, another workflow in this case, and this reads from the cache. So you write stuff to the cache, and then the other workflow will read it from there. So you are overwriting what the other workflow has written and is using. So this is exactly what needed to happen here to be able to have control. So all what the attacker needed to do was to override the cache, these 10 gigas. So in this, again, script that he had here. So instead of this curl command, now he needs to do something a little more complex, which is just run like override the cache, which he already had a tool for, and then over this cache key or one of these cache keys, just like overwrite it and overwrite node modules. And similarly, because you can now you have these node modules, you can just put whatever malicious code on the packages there, because you are going to be using the JavaScript files, let's say, that are installed there. So you can just put modify one of these or replace it with the one that actually exposes the credentials or leaks the credentials. So you are now overwriting one of these files to be able to do that. So again, this is exactly what needed to happen. So to recap, basically you needed to give the prompt injection payload to Claude, and then you needed to evict cache entries by adding more than 10 gigas, then set the poisoned cache entries with one file that actually leaks the credentials, and then wait for this job. This was a scheduled job running at a specific time every day. So just wait for it. Once this runs, it's going to leak these credentials. And now once you have these credentials, you will be able to submit your own extension as the client extension. And the extra problem here was that this nightly job was the same as, like, the credentials used for this nightly job were the same as the production one. So now the attacker even could post the full production or the stable version of Cline as well using these credentials. So this was the issue, and you'll find, let's go to this sequence diagram, which explains it pretty well. So again, like you start with prompt injection, then using this like prompt injection, you trick Cloud Code into installing this package with the pre-installed script, or you maybe use a different technique. Then you fill the cache, you basically set the poisoned entry, so a file under node modules that exposes the credentials. And then once this runs, it gets the poisoned. So this is the nightly workflow. This gets the poisoned entry, and this gives out the credentials that you need. And then you can now publish a malicious Cline update. So this is how the attack sequence worked, and how the vulnerability worked. So again, we started with this one misconfigured GitHub action, and this led to the full compromise of the VS Code extension. So let's get to the fix here. So obviously, if we go back to mitigations, so the Cline team, the first thing they did was just completely disable that issue triage workflow. And this made sense because this is not like a necessary part of the application. This was just like added to make things a little more efficient. But because the way that it was designed, as we mentioned, it was like the risk it exposed was much higher than the value it was given. So disabling it made sense. So that was the first thing. Now, obviously, if you are thinking about adding something like this, you can still use it, but maybe in a less risky way. So like we had two issues here. We had that we have allowed non-write users was exposed to everybody, and this has access to run commands and do many things. Maybe a less capable workflow would have been a little less risky, but obviously it would have been a little less useful as well. So that's one thing you need to consider. The other thing as well here is that like the nightly job no longer needs to use that cache. Now the cache makes it faster, but this is a nightly job, so even if it takes a little longer, it's not that critical. So again, it is the cache has some value, but the risk is higher as well. And the other thing as well is now, because the nightly job and the production one had the same credentials, like this made escalation easy. So using different credentials was another part of the fix here. Okay, so this is how this went. Now let's pivot to the lessons learned, in my opinion. Let's go through the things that we can take out of this when we are designing or reviewing applications, and try to reflect upon what we have seen. So I think the first thing to consider here is the fact that when we are reviewing applications, in many cases, we are missing supply chain as part of the attack surface. We don't when we are reviewing. So if you are reviewing Cline, you would look at the code of Cline itself and how it works and so on. But the supply chain, like GitHub Actions workflows, is usually missed. And this is still part of your attack surface. So that is one thing that we need to take care of here. So when we are threat modeling, when we are reviewing a service, one part which I think is really important, one important step of that threat modeling or review process, is decomposing the application and seeing what's not in the architectural diagram. So yes, you have the application code, but then you have other things. You have dependencies, you have, let's say, the cloud environment, if you have a Kubernetes cluster, if you have the container images, what packages are on the container images, if you're hosting that on something like EC2 instances, what services are running on these EC2 instances, and the supply chain as well, like how is code being pushed from developers' machines until it is actually on production. So all of these things are parts of the application that are usually missed in architectural diagrams, but are still significant when you want to review and threat model applications, because issues in supply chain, issues in the cloud environment, issues even on developer machines could lead to compromising the security of your application. So decompose your application, look at things, including supply chain, like the GitHub Actions workflow, understand who has access to these workflows, what they are triggered by, are they triggered by users that don't have permissions, and so on. So that's the first thing. Now, the other thing, and this relates to the prompt injection attack that affected the initial workflow is, again, when you are building an AI agent or a workflow that uses AI or an AI feature, you need to plan for prompt injection. And one thing I usually find useful is this mental model here, where you compare between the agent and the capabilities it has at one side and the direct and indirect user inputs from one side, and who has access to give us these inputs. So for example, this workflow had the capability to read the repo, to run commands, do a lot of things, and the input was coming directly or indirectly from users that had zero access to the repo besides read access. Like, just like they have access to the public repo, they cannot really edit it, they cannot do anything in it that is mutating, they just can submit an issue to it. So now we have a huge discrepancy between the permissions of the agent and the permissions of the person submitting the issue. And this means that prompt injection now can have huge impact. So prompt injection is not something you can fully mitigate if you are going to take any kind of user input and put it in the prompt. There is no 100% guarantee mitigation for it, but you can design your agent in a way that limits that impact. And in this case, obviously, design-wise, this opened like the permissions of the agent through prompt injection fully, and there wasn't even like a guardrail or anything of that sort that was running on user input. Sometimes maybe you can add like a guardrail, another AI agent that reads the input and makes sure it doesn't have prompt injection. Now, that being said, the way that the attacker was able to run the payload may have been missed, even because the prompt injection payload wasn't in the prompt directly. It was just like telling it to install a package, and it was a pre-installed script in that package. So the point is, you want to limit, so either want to limit the permissions of the agent or add some sort of guardrail. It shouldn't be allowed to install npm packages. It shouldn't be able to run commands, maybe like you can select which commands with which permissions and so on. And obviously, as you limit the permissions, the usefulness becomes less useful. But again, it's a trade-off that you need to take. So always think about these things: direct input, indirect input, and who is able to provide these versus capabilities. And if there is a discrepancy, then you need to plan for prompt injection and test it as well. So that's another thing that you need to do. And in this case, I think Cline took the right decision to just completely disable that workflow, because while it was valuable, the value was not proportional to the risk here. So this is something that you need to think of and take these decisions sometime. Now, the other thing is related to the cache poisoning thing. So again, this was part of how GitHub works. It's part of basically how like different workflows within the same repo share the cache. So I'm gonna go back here. So the fact here that you had this like workflow and this workflow sharing a cache, which meant that this one could poison this one. And regardless of so obviously this is really important when you have like different workflows on the same GitHub repo. But I want to also generalize this to generally when you have caching, cache poisoning is one of the things that you need to include in your threat model. So the way that you do that, you think about who can write to the cache. If it is just your process and nobody else, then okay, cache poisoning becomes less likely. But obviously in this case, because this cache is shared between different GitHub actions, so cache poisoning becomes a possibility. And you need to think about this possibility and prepare for it. And in this case, again, if the value of reading from the cache is not that high, like for a nightly job in this case, it sometimes makes sense to just not use that cache. The other thing is if there is a way to isolate the cache, so like have a cache for each workflow separately. Obviously, this is better. I'm not sure whether that's possible with GitHub, because I think in GitHub, all of the workflows by design share the cache. Maybe there is like a way to isolate it by branch or so. So it is something you need to look into. But if there is no way to isolate the cache, disabling caching becomes the more reasonable approach, or the one that is associated, like if you take the value versus the risk, it becomes the better approach to actually not use caching at all, unless you are 100% sure that the caches are isolated. So always think about the caches that you are reading from and who can write to them, and whether cache poisoning is possible and what is its impact if it does happen as well. And Another also lesson learned here is related to the fact that the credentials were shared between different releases, the nightly and the production one or the stable one in this case. So again, always try and isolate these different releases, these different environments, and use different credentials for them, because again, vulnerabilities is always possible. Proper isolation and least privilege and all of these best practices limit the impact in these situations. Like if the credentials were not shared, then this could have affected only the nightly release, not the production one or the stable one. But because they were shared, it happened. So like the impact of a vulnerability becomes higher if you don't have that isolation and least privilege applied. So I think that's like the most important things that comes to mind here. So just to recap again, GitHub Actions or supply chain generally is an important part of your security review and threat model. Always think about these. Try to think about who has access to these things, what capabilities and permissions these workflows has as well. Compare these things. Look as well if you have any kind of caching. Think about who can write to the cache and who's reading from it and what is the impact of that. So for example, in this case, we're actually reading code files from the cache, so it was even more dangerous. And again, try to apply best practices, isolation and least privilege, and so on. So these are all lessons that we can take out of this. So yeah, I found this one really interesting. I hope you found it useful as well. And yeah, stay tuned for the next videos. Have a great day all. Goodbye.